And welcome everybody to tonight's Mexico International Society meeting. Tonight's speaker is Dr. Richard Parker. Richard was born and raised in Newcastle upon Tyne. He did his undergraduate degree at Sheffield University, which included a year on the Palmer at the Isaac Newton telescopes as a student support astronomer. Richard returned to Sheffield to complete a PhD before a postdoctoral research position at the ETH Zurich, Switzerland. He returned to the UK for a Royal Astronomical Society fellowship at Liverpool John Moores, and since 2017, Richard has been a Royal Society Dorothy Hodgkin Fellow and lecturer at Sheffield University. Will you welcome me in welcoming Richard Parker with his talk on Is the Sun Special? Welcome, Richard.
Thank you very much, Paul. Good evening, everyone. Good evening, everyone online. I'm one of the last few of a Royal Society fellowship named after this person, Dr. Hodgkin. So, anyone in the room? Everyone heard of Dr. Hodgkin? No? You all heard of diabetes, right? So, diabetes, Dr. Hodgkin was the first person to figure out structural opiate. And so that was an increase on a industrial scale, and per research is going to save the lives of millions of people, probably makes the lives of millions of people today much more simpler than it was in the life. And so if anybody asks you who should be on the next 5 pound note, it's still, unfortunately, the only Brit woman is going to Nobel Prize for the whole of the science factor. That's what I know. If anybody here has research, daughters, granddaughters, and they're interested in science, please point them to Dr. Hodgkin's story. None of my research is in any way as fundamental or as important as what Dr. Hodgkin did, but what I'm going to talk about is what I do down the road in Sheffield. What I basically try and do is figure out if our sun and our solar system and our planetary system is in any way typical or what you would expect from the outcome of planet formation and all of the planets that you see in the universe. So all the planets around the stars, we've discovered 7,000-ish planets around the stars. How typical is our solar system? Put it in the context of all the other planets. This is not a picture of our galaxy, but it's an artist's impression of what our galaxy looked from the top down. And we think our sun's about 2/3 of the way out from the center. And if this is a pretty good artist's impression. If you look at every single speck of light there, they're all stars. And most of those specks of light would be groups of stars or clusters of stars. So there are billions of other stars in the galaxy, and our sun is one of many. And what we're trying to figure out is whether or not the sun and its planetary system is like any of the other stars in the galaxy. There's a lot of research that goes on into trying to figure out whether or not stuff in the center of the galaxy experiences the same physical processes as the stuff on the outskirts. If we look kind of in the immediate area of the galaxy, what we find out is that our sun's actually quite an unusual star. The reason being is that our sun is probably twice as heavy as most of the stars in the galaxy. So most of the stars in the galaxy are between about 1/10 and 1/2 of the mass of the sun. And the light that these stars produce becomes redder the lower mass they become. So the typical stars in the galaxy are typically what we call M dwarfs or red dwarfs. And they have very different properties and give off very different radiation to stars like the sun. So if we just look at stellar masses as a thing to try and characterize our sun amongst all the other stars in the galaxy, then we're already slightly unusual. We're not completely unusual in the sense that there's stars that are 2, 10, hundreds, maybe even thousands of times as heavy as our sun. But certainly a star that's our sun is a lot more massive than most of the stars in the galaxy. And then if we look at our planetary system, the first thing you do as an astronomer
because we don't have very much data and we can't run experiments in the way that biologists can or chemists can, the way we look at this is we go, okay, what is there about our system that we can quantify? What is it about our system that we can look at? And our planetary system has 4 rocky planets: Mercury, Venus, Earth, and Mars. And then we have, a bit further out, we have these gas giant planets, Jupiter and Saturn, and Uranus and Neptune. And we think that the reason that planets look like they do is that close into the sun, it's much, much warmer. And so the material around the sun is very, very dusty. And if you stick these dust grains together, you form rocky planets like ours. But if you go further out, these dust grains, when they're sticking together, these dust grains have a thin layer of ice on them. And because they have a thin layer of ice on them, that enables them to become much more massive, much heavier. And the heavier they become, the more likely they are to exert a gravitational influence on their surroundings. And things like Jupiter and Saturn become so massive that they can then accrete, they gather up gas from the disk around the sun, and they can retain that gas as well. So we think that the reason that Jupiter and Saturn are as massive as they are is because they formed further out and they were able to gather a lot of more material. And then if you go further out, Uranus and Neptune are what we call ice giants. So these, again, they formed via dust grains sticking together, and these dust grains have a thin layer of ice on them. But there's not enough gas far out at the edge of the solar system for them to become as massive as Jupiter and Saturn. So up until about 1995, that was our picture of planet formation. We thought we understood how planets form. The first planet that was discovered around a star like the Sun is a so-called Jupiter mass planet. So the story of these planets is quite interesting. So there are a bunch of Swiss astronomers in the 1980s that built telescopes that were accurate enough to detect very, very massive planets very close into the star. And people who did theory, like me, basically laughed at these guys and went, there's no way there are really massive planets really close to the star. You're wasting your time. And I don't know if you've ever met anyone from Switzerland, but they're very, very headstrong people who believe in their own kind of path and what they do. And these Swiss astronomers said, okay, fine, okay, we'll have a look for them and then we'll let you know. And then a few years later, they found Jupiter mass planets, probably even more massive than Jupiter, orbiting really, really close to the star. And the conventional theory of planet formation that explains our solar system tells you that these planets cannot form so close to the star. So something or some things must have moved these Jupiter-sized planets much, much closer to the star. And this is an artist's impression of one of these so-called hot Jupiters. So this is a star like the Sun. And if you have a Jupiter mass planet very, very close in, we expect that its atmosphere is essentially boiling. So you're boiling off the gas that is making up the most of the mass of this planet. The other thing that we've discovered, and this is much more of a problem for understanding how our solar system came to be and understanding whether or not you might find another planetary system like ours. The reason this is much more of a problem is the hot Jupiters make up about 5% of all planets. So not very many planets are hot Jupiters. They just happen to be the easiest things to detect. These planetary systems are much more difficult to explain. So Kepler was this telescope that was launched about 15 years ago and basically just pointed in one direction in the sky, in the night sky, and can measure things moving across the face of a star. So these are so-called transits. And what happens is if a planet moves in front of a star, you get a dip in the light, and that tells you that there's a body moving in front of the star. And what we found with this Kepler telescope was not just planets like Earth orbiting close to the star and moving across the face of the star, but collections of Earth-like planets. And so this is one of the Kepler systems, it's artist's impression again, but you can see we've got 7 planets very, very close to the star. And some of these planets are like Earth, so they're kind of similar size, similar mass, but other planets discovered with Kepler are what we call either super Earths or mini Neptunes. So these are planets that are somewhere between Earth and Neptune sizes, and we're not really sure what they're made of. They might be rocky planets like Earth, or they might be these gas giants like Neptune. And that's the most common type of planetary system that we know about in the universe. And this kind of poses a bit of a problem for ideas about how planets form and whether or not our solar system is similar to, or different to other planetary systems, because we didn't really expect to find so many planetary systems like these. And people are trying to explain how they came about, but it's not certainly not like a closed book by any stretch of the imagination. The interesting thing from my point of view, so this kind of comes more to the kind of thing that I work on. Young stars don't form on their own. So the sun at the minute sits in a bit of the galaxy and the nearest star is a few light years away. But it was never always like that. So the sun would have formed in the company of tens, hundreds, maybe even tens of thousands of other stars. And we refer to these sort of stellar nurseries as star clusters or star-forming regions. And we think that most stars like the sun form in these very dense regions. So to give you a kind of analogy, the sun today sits in a bit of space where I'd be stood here and then the nearest star will be right at the back of the room. Whereas a star-forming region is a bit like how you're set up in the room here. So you can reach out and touch the person next to you. Okay, so that's what a star-forming region is like. And the stars have gravitational interactions with each other, and that's important. And the reason it's important is because at the same time the stars are forming, planets are assembling around the stars. So you don't form a star and then you wait a few million years or a few billion years to form a planet. Everything's forming at the same time. And if everything's forming at the same time, then you need to understand how many times your average star might have an interaction with its neighbor. How many times might you exchange energy onto the planetary system that's forming? This, I'll point this out. So this is the center of the Orion Nebula cluster. And the Orion Nebula cluster is the kind of wispy thing at the bottom of Orion's dagger down from Orion's belt. So this is the messy object M42, which you can see with a telescope. And this is the closest star-forming region to the Earth that contains very, very bright, massive stars that we call O-type stars, which give off significant amounts of radiation and end their lives often as supernovae, and they populate the galaxy with heavy chemical elements that you and I are made of, oxygen, carbon, that kind of thing. This is R136 in the 30 Doradus star-forming region in the LMC. So LMC is a satellite galaxy of the Milky Way, and this star cluster is the most massive collection of stars that we know about, and the most massive star in that region is probably 300 times as heavy as the sun. And it's the heaviest star that we know about in the universe. So how do stars form? Well, we think that you have a cloud of gas, and that gas is stirred up by turbulence. And initially, what happens with this turbulence is you get bits of the gas cloud being compressed into what we call filaments. So you see that here, you've got these sort of yellow regions. The yellow regions represent where the gas is being pushed together, it becomes more dense. And then if we zoom in, then eventually what starts happening in these yellow filaments of gas, filament's basically a cylinder, right? So a filament of gas, and then you get over densities in the gas that then become stars, and the stars form in these little groups here. So you can see a little group forming there, a group forming there, and all the time, the stars are being funneled into each other through gravity, and you eventually get something that looks like the picture of those star-forming regions that I showed in the previous slide. As these stars are forming, there's leftover material that hasn't got onto the individual stars that's arranged itself in a disk around the star. And it's in these disks that you get planets like Earth and the other solar system planets forming. This is, this is fairly, even though this is from 2009, this is a fairly state-of-the-art simulation still. We haven't really gone much better than this in terms of, how big the star-forming region is, how many stars form. And this simulation took 2 human years to run on one of the world's biggest supercomputers. So Matthew Bate, who ran this simulation down at Exeter, I assume he found something else to do for the 2 years whilst he was waiting for this to run. But this is really, really kind of high-end theoretical or computational astrophysics in practice. And what you see at the end of the simulation is something that looks like one of those star-forming regions. And you can quantify this. You can measure the different properties of the stars and compare them to simulations, compare them to observations. Why is this important? Well, as I said, the planets are forming around these young stars, and this is an artist's impression of a planet like Earth that's forming. So initially, these planets are heated up, partially due to things colliding into them, which keeps them, imagine it, if you have magma from a volcano or lava from a volcano, the surface of these planets are very, very similar to that. And then you have interactions or collisions, bits of rock that are hanging around in the disk around the star. They collide with the planet and keep the surface molten for a few years. We can observe the very early stages of planets forming with telescopes now directly from Earth. So this is the ALMA telescope down in Chile. So ALMA is a collection of radio telescopes that are all joined you can join them all together, so that increases your observing power. And they're very, very high up and in a very, very dry part of the world. So I think the last time it rained in this desert was something like 60 years ago. So it's an incredibly dry part of the world. And the reason you need to be very dry is that the type of radiation that you observe with these telescopes is blocked out of the Earth's atmosphere by water vapor. So you want to go somewhere where it's very dry and very high up in order to observe this. When you do go that high up into that kind of dry area, you observe things like this. So this is a young star. It's about 1 million years old. It's in the nearest star-forming region to the sun. And this is the disk around the star. So this is the material that hasn't got onto the star that's arranged itself in the disk. And we think it's already starting to form planets. You see these dark regions in the disk. We think that's the signature of a planet scraping out a path around the star. And if you weren't already impressed by this image, this wasn't actually data taken with the telescope for any kind of astronomy science or anything like that. This was the engineers verifying that the instrument and the telescope was working properly. And this was the first data that came from it. There are other images since then that are even better than that. But that, I mean, this actually, this completely changed how we think about planet formation around young stars. Really, really interesting stuff. The star-forming region I showed a few slides ago, the Orion Nebula cluster, has some very bright stars in the center of it. And these stars emit so much radiation that even though planets are forming really quickly around young stars, often their formation, we think, is inhibited by radiation from the massive stars. So these massive stars give out what we call far ultraviolet radiation, so very, very strong radiation. Each photon, so each particle of radiation, if you like, is energetic enough that it can break apart a hydrogen molecule. And most of the disk of material that's forming around young stars initially is composed of hydrogen. And so this radiation is enough or strong enough to evaporate the material that otherwise would go on to form planets like Jupiter and Saturn. And if you zoom in, this is a zoom in of one of these young stars, and you can see that its disk, which is kind of this object here, is illuminated by the radiation that's coming from massive stars. And those of us who are old enough to remember the Hubble Space Telescope being launched, you might remember there was a problem with the optics of the Hubble Space Telescope when it was launched, and we had to send up astronauts in the space shuttle to fix it. This is one of the first set of images that came from the telescope once it was fixed. So well worth the effort and the money, in my opinion. And this is still, I mean, there are better images from James Webb Space Telescope, but that's only been launched for a few years. This, for many planet formation is and how they kind of operate in the same timescale, the same environment. So what does all of this mean in terms of trying to understand whether or not planets around other stars are like ours? This is work that, well, this is, first of all, this is a graph showing something called orbital eccentricity. So that's a very fancy word for talking about how circular something is. So if an orbit is circular, it has an eccentricity of 0. If the orbit is kind of oval shaped, a bit squashed, then it has an eccentricity of anywhere between 0 and 1. And then if the orbit is what we call an open orbit, like the orbit of a comet coming in once every few hundred years to the center of the solar system, that often has an eccentricity of more than 1. So our idea of how planets form, because they're forming in this kind of disk around the star, we initially expect the planet's orbits to be circular as well. And most of the orbits of the planets in our solar system are circular. So it was a bit of a shock when we started observing extrasolar planet orbits, and they have very, very high orbital eccentricities a lot of the time. So anywhere between 0 and 1. And the black points here are the exoplanet orbits. So this is how circular the orbit is. And this is how far they are away from the star. And just for comparison, the solar system planets are shown in red here. And so you can see that the most eccentric planet in our solar system of the main planets is Mercury. And we think that's due to general relativity effects because it's so close to the sun. The exoplanets have orbits that are much, much closer a lot of the time. So these are these hot Jupiters that we were talking about earlier. And then also they have very, very high eccentricities. And we don't yet have data in this area here. And that's simply because the further away a planet is from its star, the harder it is to detect. So it's not that there aren't planets over here. It's just that we haven't detected them. But the take-home message is that the orbits of planetary systems, in many cases, are very different from the orbits of the planets in our solar system. And as an astronomer, you'd want to try and explain that. So this is some work that I did when I was watching the Swiss Alps out of my office window in Zurich. This is where we put a planet like Neptune around every star in a computer simulation of a star-forming region. So you have a star-forming region, there are lots of stars in a very small volume, and because they're in a small volume of space, they interact with each other. And when they interact with each other, they can disrupt the planets around other stars. So initially we said, okay, every planet is on a perfectly circular orbit, and they're 30 times the Earth-Sun distance. So this is where Neptune is in the solar system. And what we did is you just let this computer simulation move on in time, and then we decided, well, we didn't decide, we measured what happened to the planets around these stars. And after 10 million years, that's what you see. So bear in mind, we started everything with the same properties. After 10 million years, you've got things that have moved closer into the star. You've got things that have moved further out. And then also you have things that have changed their orbital eccentricity. So they've become much less circular, much more oval shaped. So they've moved in this direction. About 10% of the planets have become what we call free floating planets. So they've been completely removed from their parent star and they've wandered around for a bit. And then a fraction of those planets then get captured around a different star. And those planets are shown by these red crosses here. And you can see that they have orbits that are kind of mixed in with the orbits of the planets that stayed around their parent star. So what you're seeing here is that planets that have had a very, very kind of dynamical lifetime. So they've been removed from the star, they've moved, and then they've been captured on another star. And they're almost indistinguishable from some of the planets that are retained around their parent star. So when you're observing extrasolar planetary systems, then they look very different to our solar system. There's a whole range of dynamical encounters, dynamical effects that could have happened to that planet. The other complication as well is that most stars don't form on their own. So we're not sure if the sun ever was in a binary or a multiple system, or whether or not it was in a binary or multiple system and then subsequently left its stellar siblings. So what happens when you're forming stars, you have a big kind of giant mega cloud of gas in space, and then that cloud of gas breaks up and fragments into what we call prestellar cores, and then the cores themselves fragment as well. And the result of the cores fragmenting often gives you a binary star system, so 2 stars orbiting each other, or a triple, so it's 3 stars orbiting the same common center of mass, or even a quadruple, a quintuple, a sextuple, etc. And a few years ago, this was the realm of science fiction. Okay, so you have things like, I'm not a science fiction fan, but in Star Wars, I believe there's a planet that orbits a double star. That's the one, Tatooine, yeah. And what you'd see if you're on one of these planets would be two suns in the sky. And this is an artist's impression of life on a planet where you have two suns in the sky, and you've got these quite fearsome looking kind of triffid plants here. But this is not science fiction at all. So the Kepler telescope I told you about earlier on, Kepler has found lots of planets orbiting the entire stellar binary system. So you've got two stars, and then you've got a planet orbiting both of them. We also know about planets orbiting a star in a binary where the two stars in the binary might be thousands of Earth-Sun distances apart, but then you have a planet orbiting at maybe 10 Earth-Sun distances around one of the stars. So this is not uncommon in star and planet formation. The thing that makes it interesting is that if you have more than one star, you've got another gravitational influence that's going to affect the planets in that system. So there's this thing called the Kozai mechanism that was named after a Japanese mathematician called Kozai. And bizarrely, almost at the same time, there's a mathematician in the Soviet Union called Lidov who was working on the same idea. And Lidov published his paper in a Russian journal, and so nobody knew about it for 50 years. But Kozai published it in one of the American journals. And so this is really called the Kozai-Lidov mechanism until about 10 years ago, when we all discovered that there was a Swedish astronomer called Hugo von Zeitbel who discovered it in the early 1900s as well. So this is now called the von Zeitbel-Kozai-Lidov mechanism. I'm going to just call it the Kozai mechanism. What it says, so Kozai basically was trying to explain there's some very odd orbits of asteroids in our own solar system, and you can only explain them if there's a transfer of energy from Jupiter onto these asteroids, but you only get that transfer of energy if there's also another massive body in the system. So Kozai was talking about the Sun, Jupiter, and then the effects on the asteroids near to Jupiter. But the physical mechanism behind this would also apply to binary stars, and in particular, if you have a planet orbiting one of the stars in the binary system. And so we think that planets would form in the same plane as the stars. So imagine you've got the Sun here, all the solar system planets basically line up in the same plane. There's not really anything kind of up there or down there or anything like that. And if we form planets in a binary star system, we expect the planets to be in the same plane. So, okay, the system might look like that, but the planets would all be in that diagonal plane there, because the disks around these stars basically align themselves with the stars. And the Kozai mechanism says that if you can somehow lift one of the stars out of its original configuration by more than about 40 degrees, then you get a transfer of energy onto the lower mass object, the smaller object. And so if you've got a binary star system, then you lift one of the stars out of the plane, then you get transfer of energy onto the planet. And this happens all the time in star-forming regions. So you've got this group of stars. Some of them will be binary stars. If they have an interaction with a passing star, even if that interaction doesn't disrupt the planets, you're still transferring the energy onto the planets. And I've got an animation. I hope this goes through the Zoom projection okay. So this is what would happen if you put the outer planets in the solar system in a binary, and then the Kozai-Lidov von Zeitbel mechanism was happening. So you're transferring energy onto the planets. So this is how circular the planets' orbits are. This is how far they are away from the Sun, and that's Jupiter, Saturn, Neptune, and Uranus. So you start off this simulation, and straight away you start to transfer energy onto the outer planet, Neptune. And because you're doing that, you're increasing eccentricity in Neptune, so how non-circular the orbit is. And because it becomes a very uncircular orbit, it starts crossing the path of the inner planets. And so it starts to cross the path of Uranus's orbit, and then eventually they eject themselves. And you can see that there's a strong encounter happening here, which is making Jupiter and Saturn librate like that. And you can imagine that this would be pretty catastrophic for anything closer into the solar system. So even if you didn't disrupt the orbits of the inner planets, you'd be throwing comets and asteroids close into the system. So that's a kind of like whistle-stop tour of the sort of stuff that I'm working on at Sheffield University. We're trying to understand how different planetary systems might be to ours and what might be responsible for those differences. The things that we know about for sure is the sun's an above average mass star. And we know from looking at planets around other stars that most planetary systems are not like ours. The reason we think is for this is that most stars and planets form in clusters. And so there's lots and lots of different physical and chemical mechanisms that are going to change the appearance of planetary systems around other stars. So dynamical interactions disrupt planets. The radiation from massive stars disrupts planets as well. And lots of stars form in stellar binaries. So you have the dynamical influence of the companion star in addition to all of the other stars that this system formed with. So thank you very much for listening. Happy to take any questions.
Richard, thank you very much. I hope people online can hear me. And I'm going to, oh no, we better leave you online for the moment. I'm going to take questions and answers, but I'm going to have to be quick. So, Andy Devey, can you unmute yourself, sir? And can we have your question, please?
Hi, Richard. First, thank you for a brilliant talk, very well delivered and really well explained. So thank you for that. Now, my question is, when you showed the summary of the 2009 visualization of the formation of stars, basically, the animation, would that process have caused like an homogenization of the gas? So the stars would have all had similar constituent properties? And if that was the case, has there been any work done to look to see if there are any siblings of the sun in the neighborhood?
Yeah, so you expect stars, I hope I'm looking at the right camera here. So you expect stars to form from the same cloud of gas to have very similar chemistry. And then what you can do is you can then look at stars like the sun and take a spectra, split the light into its different components, and then work out if they have very, very similar chemistry to the sun. That's called chemical tagging.
Right.
And there's a star cluster called M67. So it's one of the Messier objects. You can see it with a telescope. And the stars in M67 have a much more similar chemistry to the sun than if you picked a random star that's the same mass as the sun in the galaxy. So there is a theory that the sun originated from M67, which would be absolutely incredible because most star clusters disrupt within about 10 million years of them forming. So for the sun, for us to be able to trace back the sun's birth cluster would be really incredible. And also that cluster is a very, very massive cluster. So that implies that there would have been lots of dynamical interactions and lots of radiation that would have impacted the formation of the solar system. So we need to kind of figure out how likely that is. But yes, it's a kind of a technique for looking at kind of tracing the birth environment of stars that's kind of come into its own in the last 10 years or so, once we've had kind of much better measurements from telescopes.
From the simulation, does some of those stars get flung out because of the interaction?
Yeah, so you get what we call them runaway or walkaway stars. And up until about 5 years ago, we couldn't really observe these things. But we have the telescope Gaia that's been able to measure the motions of stars to a much better accuracy than ever before. And we can draw lines, literally draw lines back from stars that have been ejected from star-forming regions. So we know how many stars are ejected from star-forming regions, and we can kind of trace them back. And the other cool thing is that we can find stars that interlope. So these are stars that are not born in a star-forming region, but they just pass through it. And we can see these stars with Gaia. So it's really exciting.
And you know, when you get like double or triple stars, do they generally exert the same chemical spectra, or have some of them just coincidentally gravitationally interlocked?
So if you can form them by a capture, and in that case, you might expect them to have a different chemistry, but the chances of them forming by capture are very, very small. So most binary stars would have a similar, if not identical, chemistry.
Okay. Thank you very much. Very well
Thank you.
explained.
Thank you, Andy. I'm just looking around the room. Is there anybody in the room who wants to ask a question? Tony Morris in the room.
When you were showing planetary formation, you were showing that the planet effectively forming hot. What's the mechanism that transfers or generates the heat in the formation?
There's two things. So there's so there's gravitational contraction. Well, three things. Gravitational contraction. So initially the thing is a bit bigger, and then it contracts a little bit, and that produces heat. You also have things colliding with it. So we think the planets form from first of all, you stick dust grains together, and then the bigger things start colliding with each other, and that generates heat. The thing that I find most interesting is you also have the decay of radioactive isotopes. So massive stars produce, well, radioactive chemical elements, and some of those elements decay really, really quickly. Well, I say quickly, on million-year timescales, but that's about the timescale it takes to assemble a planet. And that radioactive decay, we think, completely dominated the early interior heating of the planets in our solar system. And we think it's responsible for plate tectonics. So we wouldn't have volcanoes, earthquakes, tsunami on Earth if it wasn't for this radioactive decay that happened early on. Now, obviously, that's, for us, it's a negative thing, right? And it often disproportionately affects the poorest people on Earth. But we don't think you would have an atmosphere and a carbon cycle that would kind of replenish the atmosphere if you didn't have plate tectonics. And so the decay of these elements that we think came from massive stars that were hanging around the sun when it was born, we think they're absolutely crucial for life to develop on planetary systems like ours. So one of the things we're looking at is, do these other planetary systems exhibit the same properties as ours in terms of their geophysical heating? Because that's a big clue as to whether or not you might expect intelligent life to develop.
So are you suggesting that planets that form round red dwarfs in an area of the Milky Way that's not dominated with large stars would have a lower chance of bearing life?
Yes, but most M-dwarf, red dwarf stars would form in a group of stars with the sun as well. So you kind of have a huge collection of stars. Some of them are really low mass, like the M-dwarfs. Some of them a bit more massive, like our sun. And they would all be subject to the same sort of heating, the same radiation fields from the massive stars. So it doesn't really rule out a type of planet formation for one set of stars versus another set of stars.
Okay.
Mike Scollard in the room.
Hi. Does nuclear ignition mark the end of the planetary formation?
Pretty much. It's not related, but basically once a star reaches the point where it can ignite in its core and start nuclear burning, that's roughly when the planets have kind of formed. And we think it's just coincidental. It takes about 10 million years to kind of assemble a planet together. And then for a star like the sun, it takes about 10 million years for it to, we call it, move off the pre-main sequence and start burning hydrogen. An M-dwarf star, like you've just been talking about, takes a bit longer. It takes about 100 million years to reach nuclear ignition. But for a star like the sun, the planet formation timescale and the nuclear ignition timescale are about the same.
Stellar flyby still happening at this
Yes,
point.
yeah.
Could this explain what moved to?
Yes, yeah. So we think hot Jupiters, you can explain in different ways. So it could be they just simply migrate in the disk as the planets are forming. And we think that actually happened in our solar system, and Saturn yanked Jupiter back. So we could have had a hot Jupiter in our solar system, but Saturn kind of moved it back. But you can also get hot Jupiters from this Kozai mechanism. So the video I showed a kind of catastrophic destruction of the planetary system, but you can also nudge Jupiters closer to the star, and they interact with the star, and it kind of drags them closer to the star and circularizes their orbit. So
I'm going to take one more question, and then we have to let Richard go. And Tony Morris's hand has gone up straight away, so we'll go over to Tony for the last question.
When you talk about hot Jupiters and the like, is there an evaporation time for these type of planets? So are we looking in a special epoch in that system formation?
I wouldn't say we're looking at a special epoch, but you're right. We can't yet. We think that there must be a lot of evaporation happening, and we think this must change the appearance of these hot Jupiters, but we still don't have observations that are kind of high enough contrast or resolution to kind of really see what the effect of that is. Obviously, ideally, you'd want the physicists I work with would want an experiment where you put a planet next to a star and see what happens to it, and then you compare it to another planet that's not near the star. Obviously, you can't do that. But what we hope to do with things like James Webb is to kind of look for clues in the atmospheres of these planets in terms of things that have been depleted. So things that have been evaporated first would not appear in the spectra of these planets if they were being evaporated. And that's kind of how you figure out how much material the planet has lost. But there's no special epoch. It's just happening all the time.
Okay. We are going to let Richard go at that point, or this point. So, ladies and gentlemen, can you join with me in giving Dr. Richard Parker a big Bexford Swinton Astronomical Society? Thank you for an excellent talk. Thank you very much.